Good morning, friends and dear students. I am here again for my course Aircraft Systems. Today I am starting my module 4. The name of this module 4 is Engine Control and Fuel Control Systems. So here we will see engine control and next we will see the fuel control systems. As you know, my name is Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As my 3 units are already completed, I have to look back for my last 25 classes which I have already covered. Today I am in lecture number 26. So today the lecture number is 26 and I am talking about principle of operation of aircraft gas turbine engines. So this is my topic, and so in this we will have this syllabus for this unit 4 is principles of operation of aircraft gas turbine engines, engine airframe interfaces, control of fuel flow, airflow. These are the topics which control of fuel flow, airflow, limited authority control system, full authority control systems. Example, power off, takes, need, types, fuel systems, characteristics, components, operating modes, fuel tank safety, fuel inserting systems. These topics I am going to cover in full module. So I am just giving the syllabus of this module, and in this module 4, these are the topics which I am going to cover. Mostly some 7 to 8 lectures will be there for this module. In today's class, I am going to see about the revision, then introduction, interfaces, engine and fuel control systems, main tank of the systems, speed and thrust control, soft speed control and thrust control. So these topics I am going to discuss. So first I am going to take about the revision of this previous classes, and in this revision we have seen that there are 4 pillars of aircraft systems. These pillars are, first is the airframe or structural system, another one is vehicle system, third one is avionics system, and fourth one is mission system. And these are the 4 important pillars on which the building of aircraft rests. So if you take the first pillar is the airframe systems or airframe and structural system. In this we have the wing, another is empennage, third one is the fuselage. Next one is the vehicle system. The vehicle system consists of the fuel system, propulsion system, flight control system and hydraulic system. So you might have seen that we have covered this hydraulic system, but these 2 things, this one and this one, will be covered in this module or the module number 4, and the flight control system will be covered on the module 5th, last module, and these 2 in the module number 4, and this is also in the module number 4. So this we are going to cover, and I am going to see that you all are aware about the propulsion system and the fuel system. And for your information, I can say that I have a 20 years of experience in aircraft fuel systems, propulsion system, hydraulic system, especially in vehicle systems and airframes and structural systems. I have a huge amount of experience. I have worked in a number of aircrafts in Indian Navy, and I know all these defects, fault analysis, investigation, accident, incidents, and how to report and how to investigate these all things. I have worked in this area sufficiently. So I am going to take about this propulsion systems and fuel system in this module. Next, another very important pillar is avionics system. In avionics system, we have the 3 subsystems. These are the navigation control, display systems and communication system. When we talk about the navigation system control, it means that aircraft is how aircraft can be navigated from one place to another place, from one city to another city. When you are flying over the sea, you cannot see anything, only water. So how your aircraft will reach to one destination to another destination? That is the job of navigation systems and the navigation control. Display means aircraft cockpit has got some display. Your pilot has to see that in which direction and what are the instruments are working and what are supposed to work. So nowadays we have very advanced systems like head-up display, then helmet mounted display, HMD and all. These all things will be discussed in the display system. Next we talk about the communication system. In communication system, we can see that how the pilot will communicate with the ground ATC or the ATC person, air traffic controller, how they are going to talk and communicate with the pilot and vice versa. So this is the process, and in this we have different types of systems like VHF, UHF, HF, LF. These all frequencies are there, and in this we have different types of equipments. Those equipments we will be going to discuss in this area. Last but not the least is the mission system, and the mission system consists of the sensors, mission computing and the weapon systems. These systems or mission systems are basically very much prominent for the military aircraft. The defense aircrafts are made for the different types of missions. It can be the fighter aircrafts, in that it can go for striker, for combat, for the dog fighting and all. And if for the peacetime, aircrafts are used for the flood relief, for the fire relief, for the patient evacuation, for the earthquake relief, or any other type of emergency in the country. The defense aircrafts are used for different types of mission, flood relief and all, evacuating the search and rescue. Then if you see about the Indian Navy, we have the maritime reconnaissance and surveillance, then anti-submarine warfare, detection of the submarine, and these all things we have to do in day-to-day routine by the help of the different aircrafts. So now I will discuss some components of the aircraft, and we have already seen that. I will start from this cockpit, the cockpit where pilot is sitting, and here all the instruments, navigation and communication equipments are fitted here. All displays are here. Then this full body is fuselage, and then we have the slats here, increase the lift. We have the spoilers here, change lift, drag and the roll. Then we have the aileron. The function of the aileron is to change the roll of the aircraft. Then we have the flaps here, here and here. These are the flaps. And here this one and this one are the ailerons. And these are the winglets, and here is also winglet. So this purpose of the flaps is to increase the lift and the drag of the aircraft. Then we have the elevator. The elevator is used to change the pitch of the aircraft. Means it will make the nose up or nose down. So like this it will make. Rudder. This rudder is deflected to make yawing towards the left side or the right side of the pilot. Vertical stabilizer, it controls the yaw. It is used to stabilize the yaw motion. Means the immediate action should not be there. If you apply this rudder, so after the deflection, it should maintain the proper position. Then we will say that aircraft is statically stable in yaw axis. Next part is the horizontal stabilizer. It is also called the horizontal tail. The purpose of this thing is to stabilize the pitch of the aircraft. When aircraft is moving, nose is moving up or the down. If you see here, aircraft is flying like this. If you want to make nose up like this, so there is a elevator. This elevator will restrict the fast motion of the aircraft. So that is the purpose of this horizontal stabilizer. Then we have the winglet. These winglets are used to reduce the induced drag of the aircraft. And you know that if these things are not there, there will be circulation, and this circulation has to be avoided. And this is done by the help of the winglet of the aircraft. Then we have the wing. The wing is the main component which generates the lift by which your aircraft is sustained in the air. Otherwise, if the lift is not there, the weight will try to pull down. So we should have minimum equal or more than the weight of the aircraft. So lift should be equal or more than the. So next is the turbo engine here. Here this you can see that turbo engine 1 and the turbo engine 2. These are the engines, and then I have completed all parts of this given. So now I will discuss about airframe system. And if you talk about airframe system, we have the three main components: 1, 2 and 3. So these are the first one is the wing, and this you can see the wing has got so many components. Like here, this is the airfoil. We have the airfoil. Then it is the center wing. Then we have the exterior plate doubler. Then we have the leading gear fitting, trailing edge, inboard flap, flaps, vane, spoilers, inboard ailerons, outboard ailerons, flaps. These all things are the part of the wing. If you talk about the fuselage we have the section 1, section 2 and the section 3, and this is the section 4. So in the section 1 it is called the forward section. Then the section 2 is called the mid section. Then section 3 is called the aft section, and this is called afterbody, and this is here the afterbody is also called the empennage. So empennage is also part of the fuselage only, but it is the last part of the aircraft. Third part is the empennage. Empennage consists of the afterbody. This is your afterbody here, and then it consists of the horizontal stabilizer. Then it consists of the rudder. Then it consists of the trim tab. So these are the parts of the systems. Now, vehicle system. If I talk about the vehicle system, this you can see here the video, how this video is moving and how this animation is done. So here this flight controls. If you see here, these are the controls here. And if you see, if you want to roll, your aileron has to go up and down. And if you want to pitch, your elevator has to go up and down here. These are the pitch here. These are the pitch here. And if you want to yaw, then you have to use your pedals. This I will show you here that how the pedals are done this work. So this you can see here that these are the pedals and these are pressed by the pilot, and the aircraft will go nose up and down. So here we have the primary flight control, roll, pitch and yaw. Just now you can see in this animation how this aircraft is moving left, right or up and down or yawing. Secondary flight controls are the high lift controls, flaprons and the slate, and then we have the speed brakes. So these are the shown here slats. This you can see here. These are the slats. These are here. If you see, these are the air brakes, spoilers. Okay, wing flaperon, Boeing 777, and all these parts are shown in this slide. Next vehicle part is the propulsion system, and we are here in the module 4, and in this we will be discussing about the propulsion system of the aircraft. So I will not go in much detail, but we should understand that the propulsion system is also part of the vehicle system. And propulsion means what? It has to pull the aircraft. It has to make the motion. So locomotion is performed by the help of the vehicle propulsion system or the aircraft propulsion system. If you see the olden days, we used to have the piston engine, and here we can see that one piston engine is this, another is different types of here, and third one is here. We have different types of piston engines for different types of aircraft, and here we have number of pistons are also very high. It may be 9 or 8 or 12 as per the power. So these are the reciprocating engine. Reciprocating engine. These are the reciprocating engine, and here we have inline, and here we have the radial type of engine. But nowadays we use a turbo engine that is called the gas turbine engine. So we have the gas turbine engine, and in this we will see that here is the compressor and here is the combustor. So first air is entering from here, it will go to the compressor, then this will be compressed here, then it will go to the combustor, and from here combustor, fuel will be burned, and this burnt fuel will enter into the turbine. So these are the turbines. So here we have 1 and 2, we have the inlet, then compression, then combustion, then turbines. So these are the parts which has to be performed. This we can see here, we have the vehicle system. In this we have the propulsion, and here we have different types of aircrafts are there. This is called the turbofan engine. Turbofan. This is the turbojet, and this is the turboprop. And here I have shown this animation and how these animations are working. This you can see here, we have here, these are the turbofans. These are the air is entering from this side, and this air, some part is bypassed from turbofan and some part is entering to the main engine. This is your main engine here. Here it is compressor is there. By the color you can see that pressure is increasing. As you see here, this is the red color, high pressure is there, and after that here the combustion will take place in this zone. This is the combustion zone, and here high temperature and the high pressure air is entering inside the turbine. So this is the zone here, 2, 3, 4, 5, 6, 7, 8. So 2 is your fan, 3 is your low pressure compressor, 4 is your high pressure compressor, 5 is your combustion chamber, 6 is the the high pressure turbine, and 7 is low pressure turbine. So here it is a basic concept of the turbine is shown by the help of this animation, which is I have taken from the internet. It is not my one. I will give the credit the person who has made this animation. Now in the vehicle system only, if you see, after this engine system, we should also have the fuel system. I will be discussing this fuel system in detail in due course of time. This fuel system provides a reliable supply, ground refueling, ground defueling, in-flight function. It gives the fuel transfer, engine feed, fuel measurement, fuel management, fuel jettisoning. So here I have shown the fuel jettisoning, how this fuel is jettisoning. If the system during landing, the aircraft is not properly balanced. So we have to make sure that aircraft is balanced during landing, and if any one side the fuel is more, that side fuel is jettisoned or it is removed, and this is done in some aircraft it is automatically, and in some aircraft the pilot will operate the jettison system and the fuel will be jettisoned. Now here it is a new topic which I am going to take you for the module 4 here. So here I am going to talk about the engine control system. This allows the engine to perform at a maximum efficiency for a given condition. So this engine control system, what is the purpose? It allows the engine to perform at a maximum efficiency. Everything should work at the maximum efficiency for a given condition. Aids the pilot to control and monitor the operation of the aircraft power plant. Originally, engine control system consisted of simple mechanical linkage controlled by the pilot, then evolved and became the responsibility of the third pilot, certified crew member, the flight engineer. So if you see the old aircraft, I have seen the IL-38 in Indian Navy, Tu-142M. Both aircrafts were having one additional person, which is called the flight engineer. This is the person who is the engineer, and he is not the pilot, but he is flying with the pilot, and he is making sure that all engine controls are working. All engine controls are working as per requirements. Okay, so engine control system consists of simple mechanical linkage previously by the pilot, then evolved and became the responsibility of the third pilot, certified crew members, the flight engineers. By moving throttle lever directly connected to the engine, the pilot or the flight engineer could control fuel flow, power output, and many other engine parameters. What is the purpose of the flight engineer? He will maintain that fuel flow is as per the requirement. Next, he will maintain that the power output of the engine as per the requirement, and many other engine parameters the flight engineer has to monitor, and he has to make sure that he or she has to make sure that these parameters are maintained inside the aircraft so that the aircraft performance is achieved as per the given standard. Following mechanical means of engine control came the introduction of analog electronic engine control. After that, one electronic engine control, analog AEEC has come, and it has made the electronic to work. Analog electronic control varies an electrical signal to communicate the desired engine setting. So it is with the help of the electric signal, it is working. It had its drawback, including common electronic noise interface and the reliability issue. So this was having the problem of the reliability issues, and also it was having some disturbance or noise which is interference due to some electromagnetic waves and some other. So now full authority analog control came in 1960. The first electronic control with the full all the parameters which can be controlled came in 1960. In the 1970, NASA and the Pratt & Whitney experienced with the first experimental FIDEC, full authority digital electronic control. What is the FIDEC? It is a full authority digital engine control. First flown on F111, fitted with a highly modified Pratt & Whitney TF30 left engine. So this is the TF30 engine which is shown in this. This is the TF30 engine, and this is the F111 aircraft. In this aircraft, this engine has got the full authority FIDEC system. That was in 1970 it was used, and this was developed by the NASA and the Pratt & Whitney of the USA. Now, electronic control system functions. What are the functions of the electronic control system? FIDEC works for receiving multiple input variables of the current flight condition, including air density, throttle lever position, engine temperatures, engine pressures, and many other parameters. The inputs are received by the EEC and analyzed up to 70 times per second. Engine operating parameters such as fuel flow, stator vane position, bleed vane position, and others are computed from this data and applies as appropriate. It controls engine starting and the restarting of the engine. This FIDEC, what is that? This FIDEC means full authority digital engine control system. This makes that starting and the restarting is controlled properly. Its basic purpose is to provide optimum engine efficiency for a given flight condition. So, another function of this thing is to provide optimum engine efficiency for a given flight conditions. It also allows the manufacturers to program engine limitations and receive engine health and maintenance reports. It allows the manufacturers to program engine limitations and receives engine health and maintenance report. For example, to avoid exceeding a certain engine temperature, the FIDEC can be programmed to automatically take the necessary measures without pilot intervention. So this FIDEC will do its own automated work. It is done, but we have to program at what type of condition this has to work. The flight crew first enters the flight data. So how it is working and how this work, your flight deck will work. The flight crew first enters the flight data such as wind conditions, runway length or cruise altitude into the flight management system. The flight management system uses this data to calculate power setting for different phases of the flight. At takeoff, the flight crew advances the throttle to a predetermined setting or opt for an auto throttle takeoff if available. The flight deck now applies the calculated takeoff thrust setting by sending an electronic signal to the engine. There is no direct linkage to open fuel flow. This procedure can be repeated for any other phase of flight. In flight, small changes in operation are constantly made to maintain efficiency. Maximum thrust is available for emergency situation if the throttle is advanced to full, but limitations can be exceeded. The flight crew has no means of manual overriding the flight deck. Means once it is programmed, flight crew will not have any control on the flight deck system. True full authority digital engine control have no form of manual override available, placing full authority over the operating parameters of the engine in the hands of the computer. So in this full authority digital engine control have no form of manual override available. The pilot or the co-pilot or the flight engineer, they don't have any authority, they don't have any interference on this flight deck system. Flight deck system will work as per the given input and no one can interfere on that. If a total flight deck failure occurs, the engine fails. That is a very drawback. So if the flight deck fails, engine will also fail. If the engine is controlled digitally and electronically but allows for manual override, it is considered solely an EEC or ECU. So what is the difference between the flight deck and the EEC or the ECU, electronic control unit? In this, the engine controlled digitally and electronically but allows for manual override. So if this system is there, then it is not called the flight deck. It is called only EEC, electronic engine control or electronic control unit. And EEC, though a component of the flight deck. So EEC is a one part of the flight deck. So if you are in the flight deck, your electronic engine control is a one part of there are number of parts in that. EEC will be one part and flight deck is controlled by fully computerized system by the flight management system of the aircraft. So what are the application of the electronic control systems? So till now we have seen that how it is operating and what are the functions and these all things, but what are the application of this electronic control system or the engine control system? Flight deck are employed by almost all current generation jet engine and increasingly in piston engines for fixed wing aircraft and helicopters. So now it is used for piston engine, for helicopters, for everywhere flight decks are used. The system replaces both magnetos and the piston engine aircraft, which makes costly magneto maintenance obsolete and eliminates carburetor heat, mixture control and engine priming. So this flight deck has made the piston engine very efficient, and because there are magnetos, these magnetos need a lot of maintenance cleaning. Every 200 hours, 300 hours of the flying, you need to remove the magnetos. You have to clean and remove the carbon or any other particles which are accumulated. Otherwise, it will give the not proper efficiency. The engine will not perform as per the required standard. These all things are eliminated by the help of the flight deck. Also, the carburetor heat. Every piston engine will have the carburetor. In the carburetor, you mix the fuel and the air. It has to give a proper ratio of this thing. And this maintenance is also very difficult. This, by using the flight deck, this all maintenance issues are solved. Mixture control, how much percentage of air and how much percentage of the fuel should be there for a required altitude and for the required power condition. These all things, and also engine priming. Before starting, we have to prime the engine. This all type of problems are eliminated once we use the FIDEC system. Since it controls each engine's cylinder independently for optimum fuel injection and spark timing, the pilot no longer need to monitor fuel mixture. So if you use the FIDEC system, the pilot need not to worry anything. Every part, every operation, everything is controlled and operated by help of the FIDEC. It may be the fuel injection, how much fuel injection is there, how much spark and at what timing spark has to be done. This makes the engine very efficient. If your timing of the spark is exactly, and your flight management system is making sure that aircraft spark is given at the required exact timing of the engine. So these all things are performed, and these applications are done by the ECS application. What are the advantages of the electronic control systems? It is better fuel efficiency, automatic engine protection against out of tolerance operations, safer as the multiple channel FIDEC computer provides, redundancy in case of failure, carefree engine handling with the guaranteed thrust setting, ability to use single engine type for wide thrust requirement by just reprogramming the FIDEC, provides semi-automatic engine starting, better system integration with engine and aircraft systems. And what are the, so these are the advantages. So it gives the better fuel efficiency. So that is the first. It means the fuel consumption is reduced. Okay, so how the fuel consumption is reduced? Because it gives a correct timing of the spark plug. Just now I told. It gives the correct air to fuel ratio. These all things make the engine very efficient. Automatic engine protection against out of tolerance operation. Suppose your engine is to operate at 400 degrees centigrade, and in case due to some problem temperature has reached to 500 degrees centigrade, it will protect. There are some mechanism, they will try to make the engine again to come down to the required limitations. Limitation tolerances should be within the limit. So that is the purpose of the FIDEC, and FIDEC make this thing perfect. Safer as the multiple channel FIDEC computer provides redundancy in case of failure. Another one is the safer. It is safe because there is a redundancy. What is the meaning of redundancy? Redundancy means if one system fail, like one it is working, another is standby system. This is the standby system. If this is the fail, then this system will operate automatically and your aircraft will be safe, your engine will be flying, it will produce the required amount of thrust. Carefree engine handling with guaranteed thrust setting. You know that at particular altitude, at particular speed, at particular weight of the aircraft, we should need a certain amount of thrust of the engine. This engine will make sure that in that conditions, your required amount of thrust is produced by the engine. So aircraft will fly at optimum conditions where the fuel consumption will be reduced and a optimum fuel consumption will be taken by the FIDEC system. Provides semi-automatic engine starting. Sometimes if you want that pilot has to be interfere during starting, there is a provision. If pilot is setting that knob, pilot can start or it will be automatic setting. This thing can be done. Better system integration with engine and aircraft systems. It makes the better engine integration with aircraft fuel systems, aircraft fuselage, wings and other things. A better condition can be achieved. So these are the advantages of the electronic engine control system. But everything is not good anywhere. If you have something good, there will be something bad. So something disadvantage also we have to see that what are the disadvantages of the FIDEC system. No form of manual override available. That is the one thing. Once it is set, you cannot do anything. Only the machine will do. Placing full authority over the operating parameters of the engine in the hands of the computer. This everything is controlled by the computer. No man interference. No interference is needed at any level. If a total FIDEC failure occurs, the engine fails. So, if the FIDEC fails, no one can save the engine. Engine is 100%, it will be go bad. In the event of total FIDEC failure, pilots have no way of manual. Pilot cannot do anything. Pilot has no option. Okay, so that is the pilot has no option. So that is the drawback of this system. Controlling the engine for restart or to otherwise control the engine. So manually controlling the engine for a restart or to otherwise control the engine. With any engine point of failure, the risk can be mitigated with the redundant FIDEC. So this risk with any single point of failure, the risk can be mitigated with redundant FIDEC. So only risk can be mitigated by the given standby system, not by the pilot. A redundant system is what? Standby systems. I have told just now. If you have the one system to operate this lever, if this fails, there is a parallel another system which will operate for the time being. This is called the redundancy. So the redundancy of this system is quite high, and in this way, so these are the some disadvantages of the. So now I will talk about something about interface. So what is the interface and how these things are working? How this your engine control systems are getting interfaced with the aircrafts. So the system here is the environment and there is an interface, and this is called the interface unit. This is the interface unit, aircraft interface. Here is the pilot. So your engine, your environment, and there is an interface. This unit is making sure that what the pilot want, that is to be obtained by the engine. Here this you can see in this cockpit, we have, here is the pilot, and this pilot is making sure that the systems are interfaced properly and he or she is able to perform as per the required standard. Interface we talk about the here, we have the flight management system. Flight management system is a very important component of the FIDEC, and here is it is a computer operated. It will take the data from air data. It will give and take from surveillance system, navigation receiver, engine and the fuel, aircraft display. I have shown here. These are the aircraft displays. Okay. So here we have the data link. Here the inertial references. Here we have the flight control. Here we have the MCDU. These are the multiple computer digital units. These are the used for interface systems. So now engine and fuel control system. Here we have to see that the following description of the engine and fuel control system explains the principles of fuel and the engine control, as well as the architecture of the most commonly used design of the fuel control system. All modern turbo fuel engines are controlled by full authority digital engine control system. Despite this large numbers of older hydromechanically controlled engines are still in use. To give an overview of these kind of system, they are described as well. So main task of the system, the main task of the engine and the fuel control system is to metering of the fuel flow to the combustion chamber under the operating condition of steady state acceleration and deceleration. The system must achieve this with the aim to keep the engine on the thrust level demanded by the pilot to prevent the exceedance of the operating limits. Limiting functions ensure the operation within the limits for shaft speed, temperature, and pressures. To accomplish this task, the engine control system also controls the function. So it has to make sure that it is functions are in the limiting speeds, temperature, and the pressure of the aircraft should be within the limit. To accomplish this task, the engine control system also controls the function of for the speed and the thrust control, how we do the speed and the thrust control of the engine. For the control principle of a turbine engine, the shaft speed and the thrust are the two most important parameters. So this speed and the thrust both are very important, two most important parameters. The simplest control system is a shaft speed control system. As long as the power lever angle is constant, it keeps the shaft speed constant. A typical application for a constant shaft speed control system is the APU, auxiliary power unit. If an aircraft engine is controlled by a shaft speed control system, the thrust will change with changing air density, and the pilot has to readjust the thrust lever to keep the required thrust constant. For the operation of the aircraft engine, a thrust control system is most suitable. Here is a pilot. Now, shaft speed control. How we control the shaft speed of the aircraft by the flight deck. In a speed control system, the shaft or the rotor speed is the main control parameter. The fuel control unit FCU uses a speed governor to adjust the shaft speed to the value demanded by the input of the power lever. This I will be discussing in detail with my own experience in the next classes as and when these things permitted. The fuel flow for the acceleration must be between the steady state line and the surge limit. For the deceleration, the fuel flow must be between the steady state and the flame out. So here this you can see we have the two limits. For this is the steady state. So if you want acceleration, it can go up to this limit. But if you want the deceleration or the reduced speed, it should not go below the flame out limits. So these are the limits which the aircraft has to maintain, the engine has to maintain, and this is done by the help of the FADEC full authority digital engine control system. It is called FADEC. This FADEC is doing this work. To adjust the calculated fuel flow to the current air density at the combustor inlet, the FCU needs at least the input of the compressor inlet temperature and the compressor discharge pressure, CDP or the PS3, additional to the N2 speed and the power lever input. With these inputs, a simple speed control system can operate. To operate as a control unit for a turbine engine, the FCU must have a minimum of functions. As an example, let us have a closer look at the hydromechanical FCU. For the operation as a speed control device, it needs to operate subsections, the fuel metering section and the governing section. This you can see by this here, the diagram. Here we have the start lever, fuel shut off. Here we have the power lever. This goes to the governing section. There is a limiting section. Here is the computing section. Here we have the metering section. Here we have the speed N2. Here we have the PS3. and here we have the temperature T25 from the engine and fuel to engine. This N2 will be observed, this pressure will be observed, and temperature. This RPM, pressure and the temperature will be sensed by this unit, that is called the flight control unit. The governing section and the limiting section, here governing section and the limiting section together form the computing section of the control unit. The fuel metering valve is moved by the control pressure from the computing section. For the governing of the shaft speed, the governing section contains a flyweight governor which receives the speed demand from the power lever. It controls an operating and the closing of the measuring valve to hold these systems. Now, thrust control of the, how we can control the thrust of the aircraft. So, for thrust control, the control system uses a main control parameter which is directly related to the thrust of the engine. This parameter can be the N1 speed of the engine, pressure ratio, EPR, which of the two is used depend on the philosophy of the engine maker. GEAE and the GCFM use the N1 speed. Rolls-Royce and the Pratt & Whitney use the EPR for this purpose. If the N1 is the main control parameter, the control system keeps the airflow through the engine constant by adopting the N1 speed of the engine. Such a control system can be based on the speed control system for the gas generator, which is supplemented by the density correction of the fan inlet parameter. The inputs necessary for this density corrections are the pressure and the temperature from the fan inlet, but this system can only adjust the high pressure rotor speeds to the changing air density. So this is the same here which I have already explained. So I am just ending here. I will talk in my next class principle of operation of aircraft gas turbine engine and the parts of the gas turbine engine. Here we have the Moir and the Seabridge. These are the references. Moir and the Seabridge, aircraft systems, mechanical, electrical and avionic systems. And next book is again from the same author, Moir and the Seabridge, design and development of aircraft systems and introduction. So if any questions, and if you want any questions in future about aircraft engines, about FIDEC, ECU and all, you are welcome to ask in this email. Okay, this is my email. You are always welcome to ask. I also request to subscribe and like this my video and this channel. Thank you very much for joining the class. I will be very soon. I will be meeting with my next class. Thank you very much for this session.
Like, share and subscribe. Hit the bell icon for more updates.